Hi there. You'll be able to find all the lectures and the worksheets that go along with the lectures if you're going to be doing them in paper form, or if you know somebody who doesn't have access to the internet and they need paper forms, tell them they can go to the high school office, and everything that I'm doing online is available in paper form at the office. So there'll be lectures and worksheets. Hopefully they'll be able to get online to see the lectures. They're on YouTube. All right. Today we're going to graph some hyperbolas, and if you graphed ellipses, you'll find that there's a great similarity between the way the equations look and the way that you actually graph them. The graphs themselves look very differently, but the approach is going to be very similar to what we did with ellipses. Student will graph hyperbolas and find the foci. We're going to not pay too much attention to the foci because of time constraints. What with the COVID-19 and whatnot, we're going to have to try to squeeze as much in as we can in a very limited amount of time. But we're going to be dealing with hyperbolas, and a hyperbola looks like two curves when you graph it. It's actually just one curve. It comes from one equation that's of this form. Y squared over a squared minus x squared over b squared is equal to 1, where a and b are going to be some numbers. You'll notice that this looks a lot like the equation of an ellipse, except instead of a plus sign, which would make it an ellipse, we have a minus sign. And the way I remember that, it may be a silly little thing that I have in my head, but to tell the difference between the equation of an ellipse and the equation of a hyperbola is the fact that the word ellipse has a ps sound in it, and so does the word plus sign. So if it has a plus sign, it's an ellipse. That's how I remember it. This doesn't have a plus sign, so it's going to be a hyperbola. When we go to graph it, we approach it very much the way we did when we were graphing ellipses. So I'll just jump straight into graphing one. These are general cases. That's a general case. That's a general case. If we were going to be looking for foci, we would use this. And that is just like the Pythagorean theorem, a squared plus b squared is equal to c squared. But we won't be doing that today. What we are going to be doing is finding the vertices, the foci, and not the foci, the vertices, the asymptotes, and we're going to be graphing. And the vertices are these points right here on the curve, the highest and lowest points for each respective curve, or these points right here and here. And I'll show you how to find those here in just a second. And here we go. We're going to find the vertices, the asymptotes, and sketch the graph of a hyperbola. Here's how we go. I look at this thing and say, all right, this is definitely a hyperbola because it has a minus sign in between it. So I'm going to approach this just like I would if I was going to graph an ellipse. I'm going to go underneath on the y-axis. I'm going to go. This is a squared, and so I'm going to take the square root of this on the y-axis, and this center is going to be at the origin, just like we did with ellipses. So I'm going to go, starting at the origin, I'm going to go up 5 and down 5 from the origin. And then on the x-axis, that's sideways motion, I'm going to start at the origin and go left 3 and right 3. Okay. Again, as we did with ellipses, we could think of this as y plus or minus 0 squared over 25 plus x plus or minus 0 squared over 9 is equal to 1. And this would tell me how far from the origin I go up and down, which would be 0, and how far from the origin I go left and right. So we can think of these like this if we want to. And this tells me from the center of the circle, which is of the hyperbola, how far we go. That's the square of how far I go up and down. That's the square of how far I go left and right. So there's the center, left 3, right 3, up 5, down 5. If this was a plus sign, I would go ahead and draw an ellipse right here and say, yay, I'm done. But because it's a hyperbola, what I'm going to do is I'm going to draw a little reference rectangle, and I'm going to go like this. I'm making it dotted because it's not actually part of the graph. It's just for reference. Because it's not an ellipse. So there's my reference rectangle. And from here, I'm going to draw the diagonals of the rectangle. And they're going to go through the center of the hyperbola there. And I'm going to extend these diagonals. They go from corner to corner. That's the diagonal. I'm going to extend them out outside the rectangle there in both directions. And here's the other diagonal. I'm going to extend it beyond the rectangle all the way to the edge of my graph. And these little lines right here are called our asymptotes. Now there are two possibilities once we get this much of the graph done. This graph is either going to look like this, or it's going to look like this. And I'm going to show you how to tell the difference. It's really simple. Whichever letter comes first, X or Y, if it's Y, the thing is going to be like this. It's going to open upward and open downward, as we say. With parabolas, we say the same thing with hyperbolas. This will open up and open down because Y comes first. Okay? If the X had come first, it would be this one, the blue one. But the Y came first, so we're dealing with this as our hyperbola right there, the green one. All right, so we've graphed it. We were going to be asked to find the foci, but we're not going to do that. The asymptotes, well, we just sketched those. That's these little dotted lines right here. An asymptote, as you may remember, we've talked about in the past, a curve will approach an asymptote and get infinitely closer and closer and closer and closer and closer. As this thing approaches infinity, this will get infinitely close and it'll never reach it. That's called an asymptotic approach. And it'll approach both of the curve will approach both of these asymptotes asymptotically, going upward and downward. So these are our asymptotes, and our curves approach them asymptotically. We want to find the vertices. The vertices are these points right here. If I were asked to define or to identify them, I would say our vertices are the points over 0, up 5, and over 0, down 5. And again, you could think of that as over 0, up and down 5. That's another way of writing it. I don't usually write it that way, but you might see it that way. Okay, so that's graphing a hyperbola that has a center at the origin. And I think I pretty much covered everything, so we're going to go on to what we do if the center is not at the origin, which is this right here. And we do it the same way. We just move the center. Let's take a look at this one. I look at this one, I'm asked to sketch it and all that happy stuff that we did up there. I look at it, I see my X is going to come first, so in my head I'm thinking, well, this thing is going to look like this when I graph it, because X comes first, it's going to look like this, instead of like this, where Y came first. X comes first, so this one's going to open sideways, it's going to open left and right. What I'm going to do is, just like I did with ellipses, I'm going to take my point, the center of my hyperbola, from the origin. I'm going to go 1 to the left and up 2. That's the center of my hyperbola there, 1 to the left and up 2. Both of these are counterintuitive, just like when we were doing parabolas back at the beginning of the year and when we were doing ellipses. These are counterintuitive. You would think it would go to the right because it's positive 1, but it actually goes to the left. And you would think it goes down because it's negative 2 with y, and it goes up, counterintuitively. So here's our center. And then from the center, I'm going to go 5 left and 5 right, because I take the square root of this number and go left and right, because x determines left and right motion. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's see if I can count correctly. And going up and down, it'll be up 4 and down 4. Square root of 16 is 4. So from here, from the center, go up 4 and down 4. Then I draw my little rectangle, a little reference rectangle. And we dot it because it's not actually part of the graph, it's just for reference. Then I sketch in my asymptotes. These are the diagonals. Make sure they go through the corners. They're not just x's floating around in the middle of space. They go from corner to corner, and then they extend on towards infinity. Or extend on infinitely. Okay, there's our reference rectangle in the asymptotes. And because x comes first, it's going to open sideways. So I come here to my vertex, and I approach this asymptote asymptotically. It'll get infinitely closer and closer and closer and never reach it. I come over here, there's my vertex, and I approach the asymptote asymptotically like that. Infinitely closer and closer and closer. And there's our hyperbola. If we were asked to state the vertices, are from the origin, we would locate it at negative 1, 2, 3, 4, 5, 6, over 6, and up 2. That's an ordered pair, negative 6, 2. This vertex, from the origin, we would find it at 1, 2, 3, 4 to the right, and up 2. That's the location of both of our vertices. And that's supposed to be a 4. That doesn't look much like a 4. Okie dokie, and that is graphing hyperbolas. Graphing them and finding the, sketching the asymptotes and finding the vertices. That's what I would like you to do. On the worksheets that I'm going to try to attach today, hopefully I'll be able to do it successfully without too many technical difficulties. It will be multiple choice. You'll have an equation, and you will have the graphs of 5 hyperbolas, and you'll just have to pick the right graph by finding the correct center and make sure it opens the right way, and make sure that the reference rectangle and asymptotes are correct. You just do that by observation. All right? So, best of luck.